Hello everyone, my name is Brendan Koenig and I'm here with Nicholas Carter, and today we're going to talk to you guys about CPU scheduling. So you might be wondering, what is CPU scheduling? Well, a CPU has to decide how it's going to divvy up the processes that it needs to complete and which order to complete them in. So that's what CPU scheduling is. It's a way for a CPU to determine the order that it's going to complete the processes that it is given. Numerous algorithms have been developed in order to efficiently schedule these processes. Of course, I'm going to be talking to you guys about these algorithms. So there are just many different styles for choosing how a CPU decides what it's going to do next. CPU scheduling is important to allow efficient system resource management. You don't want to have your system resources just sitting around doing nothing. You don't want your CPU idling for a lot of time because a process is waiting on some IO input or something like that. No, you want your process to be working, or you want your CPU to be working on processes all the time so that you get as much done as you can. So the different algorithms that we are going to be talking to you guys about today are the first come, first served algorithm, the shortest job first algorithm, priority scheduling, round robin scheduling, multi-level queue scheduling, multi-level feedback queue scheduling, and manual scheduling. So before we dive into each of these different algorithms, I'm going to go over a couple of different key terms in regards to CPU scheduling. So first, each process has the set of parameters or characteristics to it that assist the CPU in scheduling each of these processes. So the first process parameter is the start time, when the process applies for CPU access. This is used with a CPU scheduler to basically to decide when the process is going to start. If you're doing a first in, first out type of scheduling, the start time is obviously pretty important. You want to know which processes applied for CPU time first, and those are the next processes to go. The burst time is how long it takes for the process to complete. This is important in, say, for example, a shortest job algorithm, where the process that takes the least amount of time is going to be scheduled first. So burst time is important for the CPU to know how long this process is going to take. Priority level is a value given by the programmer, the user who created the process, or is just kind of a default value based on the type of process. For example, a system process is going to probably have a higher priority level than another type of process. And so we have those process parameters to kind of help the CPU decide which process it's going to do next. And then we also have these evaluation parameters to evaluate how efficient the CPU is doing. So end time is when the process last needs access to the CPU, so basically when the process completed. The turnaround time is how long the process took to complete, and it's just subtracting the end time minus the start time. And there you go. There's your turnaround time. The wait time is how long the process was holding up CPU, or not holding up CPU resources, but it's sitting and waiting to receive CPU access. The CPU utilization is how long the CPU is actively doing something. So it's a percentage, and basically it's just to measure, are we using the CPU efficiently, or is it sitting around doing nothing, and do we need to have more efficient scheduling to get good processes in there and going. And throughput is just how many processes are completed in a specified amount of time that you want to look at. If you want to look at how many processes are completed in a day or whatever, that's a measurement of throughput. And we also have some process states. These are the states that each process will be in throughout its lifetime, basically. So the first state is the new state, where a state has been created, but it's not quite ready to ask for CPU access. This is a pretty brief state, and it's the state where the CPU scheduler kind of scans it to know what its process parameters are, so it knows what to expect, what's coming up. So then the ready state is it's applied for CPU access and it's waiting its turn. The running state is when the process is utilizing the CPU resources and is doing what it needs to do, what it was designed to perform. Blocked means the process it's kind of waiting. It's waiting for an I/O response, so maybe a keyboard input or something like that. But it's waiting for some sort of response before it can continue with going on. The done process state is the process is completed. It's done everything that it needs to do, and now the CPU no longer needs to worry about what to do with it in a later stage. So there are a couple similarities between all of these algorithms that I'm going to talk about. First of all, the process parameters are read in the new state in all of the algorithms. The processes only start if a process is in a ready state. A process can't start if it's in a new state, for example, or if it's in a block state. It can't start if it's in a done state or anything like that. The only state that a process can start in is if it's in the ready state. Only one process can be ran by a CPU core at a time. It's just a CPU thing. So all of our algorithms have to keep these kind of rules in mind. So the first algorithm we're going to show you is a very simple algorithm. It's first in, first out. The first come, first serve algorithm. So whoever gets to the line first is going to be the first process to start. That process is going to run until it's completed, and then when it's completed, the second process is going to come. It has no regard for a priority level or how long the process is going to take. It just cares the order that the process is asked for CPU access. And that's kind of what this little comic shows, that some other processes are complaining that, oh crap, like this guy's burst time is really high, and it doesn't matter if your burst time is super low. It's whoever gets there first gets to sit there and use up the CPU until they're done. The next scheduling algorithm is the shortest job first. It's I guess in a way kind of close to first in, first out, sort of. It checks the burst time of each of the processes, and if at the time when the CPU is ready to take on a new process, if you have the lowest burst time, you get to go. You're up. It doesn't matter if you came in right before the CPU was looking for a new process, and there are these other processes that have been sitting there forever. It doesn't matter. If you're the shortest process, you're going first. And so this algorithm typically will result in a high throughput because the shortest processes are being done, so theoretically the most processes are being done. This of course does have a disadvantage for those long complicated processes that are going to take a while to complete, and it can be a while sometimes before these processes get CPU access, which leads to a problem that we'll discuss later on called CPU starvation. Priority scheduling uses the assigned priority value to determine what process to use. And so high priority processes will be given CPU access before low priority processes, kind of just, like maybe like a VIP lounge or something. You get access to all the best stuff where the people who paid less don't get as quality care or anything like that, or maybe on like an airplane, some sort of example like that, where you have the first class and then just the regular people didn't divvy up as much. So when you have two processes that have the same priority, you just go to a different algorithm. You either choose, maybe you choose the one that came in first. That's probably the most popular way. Or you could go with a shortest job type of algorithm. You would, I guess, combine this with one of those previous algorithms. A round robin scheduling is each process gets a certain amount of time allocated to it. And so say it gets to run for 10 units of time. After that 10 units of time is up, it doesn't matter if the process is completed or not. We're moving on to the next process. And eventually that process will get back around. It'll go for 10 more. And it'll keep going in that circle until it has completed, and then it's out of the circle. And new processes will be added to this circle. So it doesn't matter really how long you've been there, everyone is still getting an equal amount of time to access the CPU. Multi-level queue scheduling is pretty similar to priority scheduling. In this implementation, you would have multiple queues. You would have a high priority queue, like a normal priority queue, and a low priority queue. And then you could implement this kind of with a round robin format where instead of going between individual tasks, you would go with different queues. So the first stage in the round robin, the high priority queue would get, say, 30 units of time to work. Then after that is up, you would go to the normal priority queue. The normal priority queue would get a shorter amount of time, say only 20 units of time to do work. After that time, we're going down to the low priority queue, which would say get only 10 units of time. And then we're back up to the high priority queue, and we just keep going like that. So the high priority tasks get more time to get what they need to do, but the low priority tasks aren't completely shoved out of the way. They still do get some time to work, so they're not going to be completely starved out of CPU access. Multi-level feedback queue scheduling starts with everything in a first queue. Then everything in this first queue gets a little bit of time, say 10 units of time. If it doesn't complete, then we're going to move down to a queue under that. Then when we are done with all our high priority queue stuff, we're going to check the medium priority queue. Everything in there is going to get 20 units of time. Then if it doesn't complete in that, it's going to go down to our low priority queue, which is going to say get 30 units of time. So you would use a round robin format with this also. And basically this allows for the shorter processes to complete in that high priority queue stage, where the longer processes get some time, get a small amount of early access time, and then eventually they filter down to the bottom where they're going to have to wait a little bit longer, but they get a longer amount of time to use the CPU to try and complete their process. Manual scheduling is kind of a completely different thing. It's a manual schedule set by a programmer, and the process order is set. It does not change based on any changing factors. It's just set by the programmer. Each implementation is unique, and it's typically only found in embedded systems. So we have some examples. I'm going to explain what the kind of the format of this table. The first column is the process, which is just a label for each of the processes. The start time is where on the timeline the process starts. Burst time is how long it takes for the process to complete, and the priority is just a priority number, how important this task thinks that it is. This is a timeline, a pretty straightforward timeline of just time slots of CPU access. And each letter represents the process and what process is being run in that time slot. So first come, first serve is pretty straightforward. The first process to show up, the process with the lowest start time, is going to get to run to completion, and then we move on to the next process. The shortest job first, we start off running A, And then B shows up and we see, oh, B would actually complete faster if we start B right now than if we were to wait for A. So we're gonna throw A to the side a little bit. We're gonna run B, and then when B's done, we'll go back to A. So we can, in a shortest job first, throw out really long jobs in favor of shorter jobs. In a priority queue, so the first process we get is A, then we get B, and oh, B has a higher priority, so we're gonna push A to the side a bit. We're gonna run B until it's done. Okay, then A can come back. Oh, but then D comes in. D has a higher priority, so we're gonna run D until it's done, except for E comes in, and E has an even higher priority. So we're gonna run E, then when we're done with E, we can go back to D. Then we're done with D, we can go back to A, and actually we got a request to start C at time 3, but its priority is so low we just ignored it until we had everything else done. Round robin, each process gets in this case the quantum time is 1, so each process gets 1 unit of time to work, and then we move on to the next process and we keep rotating until each of the processes completes. The same thing with a time of 2. Now we're on to the next topic of starvation. This is a starvation of processes where they don't have CPU access. Has nothing to do with food, unfortunately. Starvation requires a process that's ready to go, but it has a low priority. And then it has a low priority, and we also have a bunch of processes that have high priority coming in around that low priority process. So we have a bunch of high priority processes getting ready. So this low priority process never really gets to go. It just kind of sits there. It's waiting for CPU access, but it never gets it because we have a bunch of high priority tasks that keep coming in. So we have to keep shoving that low priority task to the side. Not all algorithms have the potential for this problem. We have priority scheduling does, shortest job, multi-level, queue, and manual scheduling all have the potential for this issue. In priority scheduling, the problem is obvious. If we have a low priority job show up, kind of like C got thrown off to the side for a while. It wasn't forever. It eventually got CPU access, but that's not necessarily guaranteed if we were to keep getting a bunch of high priority jobs. Shortest job first is kind of similar, just in a different way, where we are completing the shortest jobs as they come in, so a long job might never get completed if we just keep getting a bunch of short little jobs. Multi-level queue scheduling. If a multi-level queue utilizes either a priority or shortest job first algorithm, it comes with all the problems of those algorithms as well and has the potential to also have CPU starvation. And manual scheduling is basically just a design error of the programmer who designed the list of processes and the order that they're going to be completed in. So that is our presentation on CPU scheduling.